Hi, welcome back to educator.com. Today we're going to talk about completing the square and the quadratic formula. In this lesson, we'll be working just with quadratic polynomials, that is, polynomials that have degree 2. So quadratics are of the form ax squared plus bx plus c, degree 2. A, B, C are constant real numbers, and A is not equal to 0. Otherwise, it wouldn't be a quadratic anymore because we would have knocked out that x squared. In the previous lesson, we talked all about finding the roots of polynomials. Since quadratics appear often in nature, we have to find their roots a lot. However, also from the previous lesson, we saw that finding roots and factors, it's not always an easy business to factor a polynomial. So wouldn't it be nice if there was an easier way to find the roots of a quadratic than having to figure out the exact factors and all that? And it turns out there is. This lesson is going to explore that method, what will make it easier for us. First, let's remind ourselves of something we learned long ago in algebra. Consider solving x squared equals 1. Now, our first knee-jerk response would be take the square root of both sides, and we might get x equals 1. But we have to remember that's only half of the answer. Hopefully we remembered that when we take the square root of both sides, we have to also introduce a plus and a negative version. Remember, since negative 1 squared is equal to 1 and 1 squared is equal to 1, we actually have two answers for this, x equals 1 and x equals negative 1. When you square a negative, it loses its negativeness and becomes a positive number. So if we wanted, we could express this as x equals plus or minus 1, using this symbol right here, which we call the plus minus symbol. The previous idea is given by this important rule. We have to always remember this anytime we wind up taking the square root, otherwise we'll introduce mistakes. Whenever we take the square roots on both sides of an equation when we're doing algebra, we put a plus minus on one side. So for example, if we have x squared equals 1, we take the square root of both sides, so we get square root x squared equals plus minus square root 1, at which point we get x equals plus or minus 1, which we can unfold into x equals positive 1 and x equals negative 1 are two answers. These things might get us thinking, though. It's easy to solve equations that are in this form. X squared equals k, right? We get x equals plus or minus root k. So that's pretty easy. If we could somehow get a quadratic to look like that, we'd be doing pretty well. So what if we had a polynomial like x squared minus 16 equals 0? Well, that's really easy, right? We just toss that 16 over. We get x squared equals 16. Square root of both sides. Square root of x squared equals plus or minus square root of 16. So we take the square root of both of those. X equals plus or minus 4. We managed to find the answer. Nice. So it worked really easily when we've got this x squared minus k equals 0. But this method works, works great for x squared minus k equals 0 because we just move it over and we get x squared equals k, at which point we take the square root and introduce that plus minus. But we couldn't find the roots of x squared minus 2x minus 3 with it because we can't just move it over, so that's too bad. Or could we? Maybe there is a way. So let's say a little birdie points out to us that x squared minus 2x minus 3 equals quantity x minus 1 squared minus 4. Well, at this point, it's really easy to solve for the roots now, right? We set x squared minus 2x minus 3 equals 0, and then we use this piece of information right here. We know that we can swap this and this. So we've got this right here, so we swap it out because we were told by that little birdie, and we trust that little birdie, that x minus 1 squared minus 4 is the exact same thing. So at this point, we move our 4 over. We take the square root of both sides. Square root of 4 is 2. We have plus or minus, because we have to introduce that plus or minus when we take the square root. X minus 1 equals plus or minus 2. We move the 1 over. We get x equals 1 plus or minus 2, which is equal to 3 and negative 1. We've got both of the answers for this quadratic. Great. What if there was some way that we could do this for any quadratic, right? If we could get this form of something squared minus k, it would be a cinch to find roots for any quadratic. So let's try to do this on 4x squared plus 24x plus 9 equals 0. We'll see if we can scout out a method for, we'll call it completing the square, because we're going from this form where there's a bunch of stuff to this nice thing that is squared. So we'll call it completing the square, because once we have a square minus just a constant, it's really, really easy to be able to solve for what the roots have to be. So let's move the 9 over first. We'll get 4x squared plus 24x equals negative 9. Now how can we get 4x squared plus 24x to become blank x plus blank squared? Well, there's that pesky 4 still in front of that x squared, so let's just start off by getting rid of that pesky 4. So we divide out the pesky 4, and we've got x squared plus 6x equals negative 9 over 4, right? 4x squared over 4 becomes just x squared. 24x over 4 becomes 6x, 6 times 4, 24, equals negative 9 over 4. Great. From this format, we want to get some x plus blank squared, x plus r squared. Now notice, x plus r squared is equal to x squared plus 2r times x plus r squared, right? Because x plus r plus x plus r squared becomes x times r plus r times x, so we have two r's showing up on that x, so 2r times x. X squared plus 2r times x plus r squared. We need to figure out what goes in these blanks. So we've got a blank here, x squared plus 6x plus effectively a blank, to be able to complete and get this here. So x plus blank squared. How can we do this? Well, we'll use this information that we just had here. We realize that x squared plus 6x plus 9 equals x plus 3 squared. We notice if it's got to be a blank here and it's got to connect to here, well, that was 2r here, so it must be just 1r here. So if 2r is 6, then 1r is 3. And we check this out, x squared plus 6x plus 9 is equal to x plus 3 squared. We check it, x times x, x squared, x times 3, 3x plus 3 times x, another 3x, so 6x, great, plus 3 squared, 3 times 3, 9, great, checks out. So we've got x squared plus 6x equals negative 9 over 4. That's what our equation was. How do we get a 9 on the left? Simple. We just add 9 to both sides. So add 9 to both sides because we figured out we want it to look like this. Since we want it to look like this, we make it look like this through basic algebra manipulation. Add 9 to both sides, we get x squared plus 6x plus 9 equals negative 9 over 4 plus 9. The left side is now x plus 3 squared. We collapse it. And we have that equal to negative 9 plus 36 over 4, since 9 is equal to 9 times 4 over 4, which equals 36 over 4. It connects that other negative 9 over 4 by getting a common denominator and then adding to it. So negative 9 plus 36 over 4. We simplify that and we get x plus 3 squared equals 27 over 4. Great. If we wanted to, we could easily solve this. We take the square root of both sides. We get plus or minus root 27 over root 4 equals x plus 3. Easy. We call this procedure, once again, completing the square, because we're going from a method that doesn't really have this nice squared chunk to a thing that does have this nice squared chunk, just minus some other factor or plus some other factor. We can do this in general. We can do this some general quadratic polynomial, ax squared plus bx plus c equals 0. We can do this in general and basically follow the exact same method that we just did with numbers. So first we move the c over. Just like we moved 9 over, we have negative c now. Since we eventually want something of the form x plus blank squared, we don't want this pesky a getting in the way, so we divide both sides by a. B divided by a becomes over a. Divide by a becomes just a 1 in front of that x squared. Divide by a over here. So negative c over a, great. So we get x squared plus b over a times x equals negative c over a. All right. Next, our goal is something of the form x plus blank squared. Now we notice once again, x plus r, whatever r is, squared equals x squared plus 2r times x plus r squared. Now we want to match up to this format. We already have b over a times x. So we want 2r times x, right? The x squared here matches with the x squared here. The 2r times x here matches with the b over ax here, and the r squared that we haven't introduced yet is what the blank is that we don't know what we're going to put in yet. So if 2r is the same thing as b over a, if b over a equals 2r, then that means b over 2a equals r. So now with that in mind, we know what we want to introduce is r squared. b over 2a equals r, so we want to add r squared or b over 2a quantity squared to both sides. So we add r squared equals b squared over 4a squared, and we complete the square. X squared plus b over ax plus b squared over 4a squared. That collapses into quantity x plus b over 2a squared. Check that out real quick. X times x becomes x squared. Great. X plus b over 2a, x times b over 2a becomes b over 2a times x, plus, it'll happen a second time, so b over 2a plus b over 2a becomes 2b over 2a, so just b over a still times x. B over 2a times b over 2a becomes b squared over 2 times 2, 4, a times a squared. So b squared over 4a squared, great, checks out. And we added this b squared over 4a squared to both sides. Can't just add it to one side. And so that will collapse into b squared minus 4ac over 4a squared, because we've got negative c over a. So that becomes negative 4ac over 4a squared. So we can get them on a common denominator. So we've completed the square. Great. That is a general form. At this point, we've shown that any equation that starts off as ax squared plus bx plus c equals 0 is equivalent through completing the square to this equation right here. It's a little bit complex, but we just proved that we can just do that through basic algebraic manipulation. At this point, it would be quite easy to solve a given quadratic for x by plugging in values for a, b, and c, then just doing a little algebra. For example, if we have 4x squared plus 8x plus 2, then our a is equal to 4, our b equals our 8, and our c equals our 2. Now, what the heck, let's color code that. So a at 4 is red, b at 8 is blue, and green, c equals 2. Lovely. So this is x plus b over 2a. So our a's are the red things, our blues are the b's, and our c is that green. So we follow this format. And we've got blue 8 here, 8 squared here. Our a's 4 here, and 4 here, 4 here. And then finally our green here. And this coefficient here just stays here. This coefficient here just stays here. This coefficient here just stays here. So if we wanted to at this point, we could just, do some arithmetic, and we'd be able to simplify that, and then we'd be able to take the square root and basically just be able to solve for it, and we'd be able to get the answer. But we can go one step farther, and we can just set up a general formula to solve any quadratic ax squared plus bx plus c equals 0. We're so close to this, and then we can just use that formula in the future anytime we want to find the roots of any quadratic. So at this point, we've shown that ax squared plus bx plus c equals 0 is the same thing. It's equivalent to the completed the square version of x plus b over 2a quantity squared equals b squared minus 4ac over 4a squared. So we just take the square root of both sides to get to the x. X plus b over 2a equals plus or minus square root of b squared minus 4ac. What is the square root of 4a squared? 4 comes out as 2, a squared comes out as a, so we get the 2a on the bottom. So x plus b over 2a equals plus or minus square root of b squared minus 4ac all over 2a. Next, we isolate for x. We subtract by the b over 2a plus or minus square root of b squared minus 4ac all over 2a. Hey, look, they're already in common denominators. So we get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We have the quadratic formula, an easy way to solve for the roots of any quadratic polynomial. So as long as we've got some quadratic polynomial like this, we just plug into this thing and do some arithmetic. Might get ugly, might require a calculator, might not be, really easy arithmetic, but there's not much thinking that we have to do. There's no difficult cleverness of figuring out just the right way to factor it. We just plug and chug and an answer will pop out. Now, I'm not a big fan of memorizing a lot of stuff. I think for the most part you want to understand how to get to these things, but the quadratic formula is going to come up so often. You're going to wind up needing to see this negative b plus or minus square root of b squared minus 4ac all over 2a. I'm going to have to recommend you probably want to memorize this thing. Memorize the quadratic formula because it will show up a lot. And even if your teacher doesn't absolutely require you to have it memorized in another class, you're going to wind up seeing this so often, and you're going to have to solve for so many quadratics that you want to just have this in your back pocket so you can pull it out anytime. You'll just remember and go, oh yeah, I'm trying to look for the roots of a quadratic. I can solve this through the quadratic formula. It comes up a lot, so it's good to just have it memorized. All right, follow the format if you're going to use the formula. It's really important to note that if you want to use the quadratic formula, the polynomial must be set up in this format. Ax squared plus bx plus c equals 0. Absolutely has to be set up in this format. For example, if we have 2x squared minus 47x plus 23, then our a equals 2, our b equals negative 47. Because notice that here it is a plus, but here it's a negative, so it must be a part of the number. And then finally, our c equals 23. So a equals 2, b equals negative 47, c equals 23. Great. But it would be totally wrong, absolutely wrong to say x squared plus 3x minus 4 equals negative 2x plus 8 gives us a equals 1, b equals 3, c equals negative 4. We've got this equals stuff over here, right? It has to equal 0, otherwise it doesn't work. It has to be in this format of ax squared plus bx plus c equals 0. That's how we derived completing the square. That's how we derived the quadratic formula. If it's not in this format, it breaks down entirely. We can't use the quadratic formula. So we have to put it into this format before we can use the quadratic formula. Absolutely has to be in the form, otherwise it just doesn't work. How many roots does a quadratic have? Now, of course, not all quadratics have the same number of roots. The graphs below show the 3 possibilities. We've got one where it intersects it twice, one here, 2 roots. We've got it where it intersects it just once, it barely grazes and touches, barely just hitting it once. Or we've got absolutely none, where it never manages to cross the x-axis. And of course, these could all flip the other way, right? We could have it going down this way, we could have it barely touching on this side, and we could also have it crossing over like this. There's no guarantee that it has to be pointed or look like these, but the idea is just these are the number of times it could cut. It could cut on both sides, cut just once at the tip, or not at all because it never manages to cross it. So the quadratic formula actually manages to show us which one of these situations we're in. The way we do this is through the discriminant. Remember the formula, negative b plus or minus b squared minus 4ac all over 2a. You're going to hear that a lot. Good to memorize. The expression b squared minus 4ac is the discriminant. It tells us how many roots there are. B squared minus 4ac means that there are 2 roots. Sorry, b squared minus 4ac being greater than 0 means that there are 2 roots. If it is equal to 0, then we have 1 root. And if it is less than 0, we have 0 roots, each corresponding to those colors on the last picture as well. So the discriminant tells us how many roots, what kind of situation we're in for how often our parabola is going to actually manage to cross over that x-intercept, touch that x-axis. Why or how does it work? What's going on here? So let's look at the quadratic formula once again. Remember, our discriminant is the b squared minus 4ac part, the part underneath the square root. So it's under the square root. Each of the 3 cases we just saw correlates to how many answers come out of the square root. We've got this plus or minus here. So if b squared minus 4ac is positive, 2 are going to come out because of the plus or minus, right? If we've got square root of 4 in there, then we've got plus 2 and minus 2. Square root of 4, 2. So we've got plus or minus 2. So we've got a plus version and a minus version. That's 2 different worlds, so we get 2 different answers. But if we've got b squared minus 4ac equals 0, then plus or minus 0 is just 0. So either way, it's just the same world. Square root of 0, so plus or minus 0. Doesn't really matter if we go with plus or the minus. We get the same thing. So we've just got 1 root. Only 1 possibility. Finally, if b squared minus 4ac is negative, that is less than 0, square root fails entirely, so there are no answers. It's impossible to take the square root of a negative number, remember, because any positive squared becomes positive, any negative squared becomes negative, so there's no number out there that when you square it will become a negative, so there's no answers if b squared minus 4ac is negative. At least there's no real answers. We'll talk about how things get a little shady once we get to the complex numbers, but for right now, discriminant tells us no answers if b squared minus 4ac is negative. Really, we can just look at how does this interact with square root. How many things can come out of plus or minus square root? If 2 things can come out because it is a positive number to the square root, then we've got 2 possibilities, 2 answers. If 0 is under the square root, then there's 0 possibilities. Sorry, there's 1 possibility because it's just 1 possibility underneath square root of 0. So plus or minus 0, just 1 thing. If it's plus or minus square root of a negative number, then that's impossible to do in the first place, so we've got no possibilities under it. We have no answers. All right, we're ready for some examples. Complete the square on the polynomial 3x squared minus 30x plus 87 to give an equivalent expression. Now, we didn't formally talk about completing the square when it wasn't equal to 0, but we can follow the exact same method. 3x squared minus 30x plus 87. First thing we do is we want to sort of look at that 87 as being off on the side. It's still part of the expression, but it's not what we really want to work with fundamentally. Now, we've got a 3 in here, so we want to pull out this 3. We'll pull it out. We get 3 times quantity x squared minus 30 pulling out a 3 gets 10x plus 87 still over there. 3 times quantity x squared minus 10x. We check, yeah, checks out. We're still the same thing there. Next step, we want to figure out plus blank. What blank is going to go in there? Well, remember, if it was x plus r squared, then that would become x squared plus 2r times x plus r squared. So who makes up our 2r right now? Our 2r here is our negative 10. So if 2r equals negative 10, then our r by itself would be equal to negative 5. So we want to get a 25 inside. So we've got 3 times x squared minus 10x plus, we want r squared equals 25. Negative 5 times negative 5, 25. So plus 25 on the inside. So we want that to show up. Of course, if we just change our expression around, we just put a number in there, it's not the same expression, we just broke our mathematics. It doesn't work like that. So we have to make sure that however much we put in on one place, we take out of somewhere else, right? I can have any number, 5, and I could add 3 and subtract 3, and it would have no effect. I'd still be left with 5 because it's the same thing as adding 0. So if we add 25 into the inside of our quantity, how much do we need to take away on the outside? Well, putting in 25 on the inside, remember, it's 3 times quantity stuff plus 25. Well, that is going to be stuff plus 75, right? 3 times 25, those two connect like that. 3 times 25 means we need to take away 75 on the outside to keep the scale, to keep our scale balanced, right? We put 25 into the inside of the parentheses. 3 times 25 is 75, so we need to take 75 out. We put a total of 75 into the expression, so if we take a total of 75 out, our scale remains balanced. Minus 75, and then we still have to bring on what was in the expression before, plus 87. So 3 times x squared minus 10x plus 25, x plus r squared, our r equals negative 5, so we've got x minus 5 squared. Let's check and make sure that's still correct. X squared, x times x, x squared. X times negative 5, negative 5x, negative 5 times x, negative 5x again, so double that, negative 10x, checks out still. Negative 5 times negative 5, 25, great, checks out. Minus 75 plus 87, minus 75 plus 87, that cancels down to, not cancel, but becomes plus 12. And now we've got something that is equivalent. 3 times quantity x minus 5 squared plus 12. Let's check to make sure that's correct. 3 times x minus 5 squared would become x squared minus 10x plus 25 plus 12. 3x squared minus 30x plus 75 plus 12. 3x squared minus 30x plus 87. Great. Checks out. That's the same thing as what we started with. All right, next one. Second example, solve negative x squared plus 10x minus 20 equals 4x minus 16. So we've got that nice fancy quadratic formula. Let's take it for a spin. First thing though, it's not currently equal to 0. So it's not set to 0. So we need to get the whole thing so it looks like that. Ax squared plus bx plus c equals 0. So let's move things around. We subtract by 4x. We add 16. We get negative x squared plus 6x minus 4 equals 0. Great. So we're now set up. So we've got a equals negative 1, b equals 6, c equals negative 4. We're in that format, right? Our normal format is ax squared plus bx plus c equals 0. So we've got that parallel. What is our formula? The roots are going to be x equals negative b plus or minus square root of b squared minus 4ac all over 2a. All right, so we start plugging into that. We've got x equals, plug in our blue negative 6, plug in our b, plus or minus square root b squared, 6 squared, minus 4 times a, negative 1, times c, negative 4. Keep that going. Colors are getting a little bit funky here, but basic idea going on still the same. Negative 6 plus or minus square root, so 2 times, and the red one here, a. And notice these coefficients, they just stick around the whole time. Minus 4, minus 4. They just stick around no matter what. The plus or minus moves down. The negative moves down. So those things are always there. At this point, all we have to do is solve it out. So x equals negative 6 plus or minus square root of 36. Negative 4 times negative 1 times negative 4, 2 of those cancel out, but we're still left with a negative, so minus 16 over 2 times a, oh gosh, sorry, 2 times, we're going to replace that with what it should become, 2 times negative 1, got confused by all the colors. 2 times negative 1 becomes negative 2, so we have x equals negative 6 over negative 2 plus or minus the square root of 20 over negative 2. X equals, this becomes positive 3 plus or minus the square root of, what's 20? Square root of 20 is equal to square root of 4 times 5. We get 2 root 5. So we replace that down here. So we've got 3 plus or minus 2 root 5 all over negative 2. So that's 3. Now the negative here hits that plus minus, but all that's going to do is cause the plus to become a negative and the negative to become a plus, so it didn't really do anything. Plus minus the same thing as minus plus. So we're basically where we were before, root 5. So our answers are going to be x equals 3 minus root 5 and 3 plus root 5. Those are the solutions to that because we found the roots to when we turned it into the format that we could use it on. Great. A man standing on the top of a 127-meter tall cliff throws a ball directly down at 10 meters per second. The height of the ball above the ground is given by height at time t equals negative 4.9 t squared minus 10t plus 127, where t is in seconds. How long does it take for the ball to hit the ground? So we've got this guy. He's standing on top of a cliff. And for some reason, he throws a ball down, right? Ball's going down. So it's moving down towards the ground down here. So let's see, what does this mean? Where is he? What is it going to be? What is ground, right? So ground is h equals, what does that mean? Well, we notice if we plug in 0, then that's going to be just as he threw it, which would, the zeros would cancel out the t here, and we'd be left with just 127, which is where he starts at, right? 127 meters high. So that makes sense that the ground is going to be 0 meters high. Makes intuitive sense. So we know what we're looking for is when the ball hits the ground. When does the ball hit the ground? The ball hits the ground at h equals 0. That's what the height we're looking for is. Ground is normally put at h equals 0. You can sometimes move it around, but for the most part, you'll wind up seeing in any word problem where they're talking about the height, ground level, normally whatever our base level is considered, is a height of 0. How long does it take for the ball to hit the ground? Well, that means if we're looking for when h equals 0, then we're going to use that in here in our function. So 0 equals negative 4.9 t squared minus 10t plus 127. So we plug this into our quadratic formula. We're not looking at x anymore. We're looking at when t is going to give our roots. So t equals negative b, negative 10, plus or minus square root of negative 10 squared, minus 4ac, 4 times negative 4.9 times 127, all over 2a, 2 times negative 4.9, t equals positive 10 plus or minus square root of 100 minus, that'll wind up, we worked that out with a calculator, 2489.2 over negative 9.8. So at this point, you know, that's not super easy to work out. So we're going to start plugging into a calculator. We won't actually do that here, but we're going to basically plug 2 different expressions into our calculator. The plus version, square root of, so that will be, one thing I screwed up there. That was negative 4 times negative 4.9, so it becomes plus. Otherwise, it'd be impossible because we'd have a negative underneath our square root. That's what made me catch that. 2589.2 divided by negative 9.8, and 10 plus 10 minus square root of 25.89.2 over negative 9.8. We plug that into our calculator and we get 2 different answers. T equals negative 6.213 and 4.172. Now, first, that should, set off some alarm bells in our head, right? We throw a ball down a cliff. We imagine this in our head. That's the very first step, is we imagine our head. You throw a ball down some tall height, and eventually it hits the ground, right? That's the end. It doesn't hit the ground at 2 different times. And so what does this mean? We've got 2 different answers here. So which one is the correct answer? Negative 6.213 or 4.172? Which one's right? Well, we think, okay, we know that this is t given in seconds. So we know what happens. He throws the ball down, and so forward in time, it's falling. We're going by this equation. But what about a negative time? Did he throw the ball before 0 seconds? No, he throws the ball at 0 seconds. It starts at his height at 0 seconds. So it must be h of t is only true, its domain is only 0 to positive infinity. And it actually is not even going to be true after 4.172 because all of a sudden the ground gets in the way and stops this equation from being true. So h of t is only true from t equals 0 until ball hits ground, until whatever t ball hits ground at. So that's sort of an implicit thing that we hadn't explicitly stated, but we had to understand what's going on, because otherwise we'll get 2 answers and one of them is going to be wrong. We have to realize what's going on. We don't want to just blindly do what the formula told us. We want to think about what does this represent. Word problems require thinking. So negative 6.213, 4.172, we realize it's only true from t equals 0 to higher numbers until the ball hits the ground. So the ball hits the ground at 4.172, and negative 6.213 is an extraneous solution. It's impossible to look at those times because that's back before this formula, before this function ever wound up even being used. The function comes into existence only once the ball is thrown at time t equals 0. So negative times are completely extraneous. We can't use those answers. And we get 4.172 seconds as the correct answer. Great. Final example. 2 cars are approaching a right angle intersection on straight roads. The first one is coming from the north at a constant speed of 30 meters per second, while the second is from the east at a constant speed of 25 meters per second. If both cars are currently 200 meters from the intersection, how much time until they have a distance of 90 meters between them? Oy, right? This is like the classic nightmare word problem of like so many things here. What are we going to do? Well, we just start figuring out what is it telling us, then we'll work on the math. So first thing we do, we try to make a picture. So right angle intersection. So we know what it looks like, an intersection looks like on the street, right? 2 streets intersect one another. We know that they came together at a right angle because it says right angle intersection. Great. They're on straight roads, so we're guaranteed the fact that straight lines come out of it, so this makes sense. The first one is coming from the north. Well, let's put north as being this way. So this car is up here. It's coming from the north at a constant speed of 30 meters per second. So it's going down 30 meters per second. Where is it right now? We know it is 200 meters away at the start. What about the other one? The other one is coming from the east. So east will be over here. And it's going at 25 meters per second. How far away is it? They're both cars, so we figured out the 200 meters to get the first one. Both cars, currently 200 meters, so 200 here as well. How much time until they have a distance of 90 meters between them? So we also want to be able to introduce so I guess the other thing we have to figure out is what does it mean for distance between them? So if we've got a point here and a point here, then the distance is just the distance between those 2 points, right? But we don't have any information about the distance between them, right? We're not told how far away they are. But we are told how far they are from this intersection in the middle, right? So this, if we've got here is x and here is y, oh, hey, look, we can use the Pythagorean theorem, x squared plus y squared equals d squared. Great, so we've got a way of relating these 2 things. But if we're just frozen at 200, 200 squared plus 200 squared equals distance squared, then we're going to get something that's never going to be 90, right? Because we're just looking at a single snapshot in time. So we also have to have a way of their movement, their motion affecting this. So they start off at 200 away, but then they start to get closer and closer to that intersection. So it's going to be 200 minus 30 times t, because it's going to be as they get closer to the intersection, as more time goes on, more of their distance from the intersection will disappear. So 200 minus 30t. And then the other one is 200 minus 25t, because the red one, the north car, is coming at 30 meters per second. So for every second that goes by, it will have moved 30 meters towards the intersection. So it will be 200 minus 30t. And the blue car, the east car, will be 200 minus 25t, because for every second it moves 25 meters towards the intersection, 200 less 25 meters. Okay, so at this point, we've got a real understanding of what's going on. We can now put this d in here, and we can connect all these ideas. So we've got 200 minus 30t is what describes the red car, our north car, and 200 minus 25t is what describes the east car, our blue car. And we're looking for when is the distance equal to 90. So remember, we had x squared plus y squared equals d squared off of the fact that, this is just a nice, normal Pythagorean triangle. We can use the Pythagorean theorem here. Square of the two sides is equal to the square of the hypotenuse. So we've got 90 squared equals quantity 200 minus 30t squared, our red car, our north car, plus 200 minus 25t squared, our east car, our blue car. Great, and now we're trying to solve this, figure out when is t going to make this true. At what t will that equation there be true? So we just start working it out. Now this is going to get pretty big pretty fast because we've got big numbers, but luckily we've got access to calculators in this world. So 90 squared, plug that in, that comes out as 8100. 200 times 200 becomes 40,000. Minus 30t, 200 times negative 30t, plus negative 30t times 200. 200 times negative 30t is negative 6,000, but we have to double that, so it's minus 12,000t, minus 30t times minus 30t, plus 900t squared. The next one, so plus 40,000 again for the other portion. 200 times negative 25 becomes minus 5,000, but then we also have to have negative 25 times 200 again the other way, so it's negative 5,000 doubled, so minus 10,000t times, plus negative 25 times negative 25, so plus 625t squared. All right, we simplify this, get this into, this looks like something that could eventually turn into a quadratic, right? So we go, time to use the quadratic formula. So we need to get it into that form. We'll subtract 8100 over. So 0 equals, so minus 8100, minus 8100 over here. So we look 625t squared plus 900t squared. We get 1525t squared. Next, minus 10,000t, minus 12,000t, minus 22,000t, 40,000, 40,000, minus 8,100, plus 71,900. Oi! But we're in a position where we can now use the quadratic formula. Once again, it's a good thing that we have calculators, otherwise this would be really difficult, but we can use the quadratic formula now. So t equals negative b, so negative 22,000, so 22,000, plus or minus the square root of b squared. So 22,000 squared, we'll drop the negative sign just because it's going to get squared anyway. 22,000 squared minus 4 times 1525 times 71,900. At this step, we might toss those parts in, just the part underneath the square root, use the discriminant, make sure there is an answer. It will turn out that there is an answer, so we'll just keep going. And that's going to be divided by 2 times 1,525. I won't work this all out here. I'm going to trust the fact that you can do the two different versions. Remember, there is a plus version, and then there's a minus version. So we do both of the versions, and we will wind up getting t equals 5.004 seconds and 9.423 seconds. So in the last one, the problem with the falling rock, where he threw the rock down the cliff, there was only one answer that was true out of the two things that came out of it. But what about this one? Is one of them wrong and the other one right? Is it only possible for one of them to happen first? Well, if that's the case, if we're only looking for what is the time, the immediate time, the soonest time when they are 90 meters away from each other, then it's 5.004 seconds. However, if we think about what's going on, let's try to visualize this, right? So we've got car in the north, car in the east. They start off very far away from one another. But as they get closer and closer to one another, at some point their distance is going to, right, this one's going faster, this one's going slower, but they're going to pass so that their distance is close enough for it to be like ding, 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 5.004 seconds. They are now 90 meters away. Now they pass and they wind up being very close briefly, but then they keep going. And at some point on the reverse side, their distance begins to grow now after they pass the intersection. So they actually start to get farther away. So after they pass the intersection, eventually it's going to be ding, 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 ding. They are now 90 meters away from one another once again at 9.423 seconds. And then if they keep going on and on and on, they'll never wind up being 90 meters away from each other. But this is the first time they are 90 meters away, and then this is the second time. Now, it's quite likely that a question phrased in this way would only be asking for the first one, but we are actually able to find out both of the times that they are 90 meters away, assuming they maintain constant speeds and straight roads. Pretty cool. All right, hope you've got a good sense of how to complete the square and how important and useful the quadratic formula can be. Make sure you memorize it. I know I hate memorizing things too, but it winds up coming up so often you really have to have it memorized. Negative b plus or minus square root b squared minus 4ac all over 2a. Make sure you get that one burned into your memory because it will show up a lot. And we'll see you later next time. We'll talk more about the general nature of quadratics and parabolas and see how what we just did in this lesson will wind up connecting to that one as well. See you at educator.com later. Bye.